Welcome to Dreaming Through Knowledge, where science becomes calm. Tonight, we embark on a journey that is not about the distance of space, but the depth of time. We are going to travel back to the very beginning of our own story. We are going to witness the birth of the ground beneath our feet. We are going to explore the formation of the early Earth. But before we drift into the deep past, I invite you to subscribe to this channel and perhaps leave a comment below. Tell us where you are listening from tonight and what time it is in your part of the world. It is a small way for us to connect our own locations in space and time before we lose ourselves in the vastness of the primordial solar system. Now, let your body settle. Let the gravity of the modern Earth hold you. That force, that heaviness you feel pressing you into the mattress, is the subject of our story. It is the force that gathered the world from dust. To understand the Earth, we must forget the Earth. We must wipe the image of the blue marble from our minds. We must erase the white clouds, the green forests, and the deep oceans. We must erase the moon. We must even erase the solid rock. We have to go back to a time when the Earth was not a place, but a potential, a cloud of possibility floating in the dark. We travel back 4.56 billion years. We find ourselves in a region of the galaxy that is dark and cold. This is a molecular cloud. It is a vast nursery of gas and dust, stretching for light years across the spiral arm of the Milky Way. It is silent here. The density of the gas is incredibly low, a few thousand atoms per cubic centimeter. To a human, it would look like a perfect vacuum. But on a cosmic scale, it is a rich reservoir of matter. It is filled with hydrogen, helium, and tiny traces of heavier elements, carbon, silicon, iron, forged in the hearts of stars that died long before. These heavy elements are dust, microscopic grains of soot and sand, frozen in the cold. They are the ashes of the ancestors, and they are waiting. For millions of years, this cloud drifts. It is in equilibrium, balanced between the outward push of its own weak heat and the inward pull of its own gravity. It is a sleeping giant. But then, something disturbs the sleep. Perhaps a nearby star explodes as a supernova, sending a shockwave rippling through the dark. Or perhaps the cloud drifts through a density wave in the galaxy. Whatever the cause, the balance is broken. A pocket of gas gets squeezed. Gravity wakes up. The denser region begins to pull on the surrounding gas. It draws it inward. The collapse begins. What was once a vast, amorphous cloud begins to shrink, and as it shrinks, it begins to spin. This is the law of conservation of angular momentum. Just as a figure skater spins faster when she pulls her arms in, the cloud spins faster as it contracts. It rotates, and as it rotates, it flattens. Gravity pulls everything toward the center, but the spin pushes everything outward at the equator. The result is a disk, the protoplanetary disk. It is a flat, swirling wheel of material, billions of kilometers wide. In the center of this disk, the material is crushed together. The pressure rises, the temperature skyrockets. A ball of gas forms, glowing with a dull red heat. This is the protostar. This is the infant sun. It has not yet ignited nuclear fusion. It is not yet a true star. It is powered only by the heat of its own collapse. But it is hot enough to light up the disk. It casts a warm, orange glow over the rings of dust and gas that circle it. We are standing in the future location of Earth. But there is no Earth here. There is only the solar nebula, a thick, dusty haze. If you were floating here, you wouldn't be able to see the stars. You would be inside a sandstorm of cosmic proportions. The temperature here, at 1 astronomical unit from the center, is hot, perhaps 1,000 degrees Kelvin. It is too hot for ice. Water cannot exist here as a liquid or a solid. It is only steam. Methane and ammonia are gases. The only things that can remain solid in this heat are rocks and metals. This creates a boundary in the solar system known as the frost line, or the snow line. It lies out beyond the orbit of modern Mars. Inside this line, where we are, the planets will be made of rock and iron. Outside the line, where it is cold, they will be made of ice and gas. We are in the zone of the terrestrial planets. Let us look at the dust. These are the building blocks of our world. They are tiny, microscopic, grains of silicate, the stuff of sand, grains of carbon, the stuff of soot, grains of iron. They are floating in the tenuous gas of the disk. They are orbiting the young sun, traveling at tens of thousands of kilometers per hour. But because everything around them is moving at roughly the same speed, the collisions are gentle. Imagine 2 specks of dust drifting toward each other in a sunbeam. They touch. They do not smash apart. They kiss. At this scale, gravity is too weak to matter. A grain of dust has almost no gravitational pull. So why do they stick together? They stick because of electricity, electrostatic forces. The same force that makes a balloon stick to the wall, or dust stick to a fan. Blade. The grains have tiny electric charges on their surfaces. When they brush against each other, they cling. This is the first step of planetary construction. It is not violent. It is the formation of dust bunnies, fluffy, porous aggregates of cosmic lint. These clumps grow. They sweep up more dust. They become the size of a grain of sand, then the size of a pebble, then the size of a rock. As they grow larger, the physics changes. They begin to interact with the gas in the disk. The gas exerts a drag force. It is a headwind. The gas in the disk orbits slightly slower than the solid rocks because the gas is supported by its own internal pressure, while the rocks are supported only by their orbital speed. This means the rocks are constantly plowing through a slow-moving wind. This headwind saps their energy. It slows them down. And when an orbiting object slows down, it falls inward. This leads to a problem that puzzled astrophysicists for decades: the meter-size barrier. The math suggested that once a rock got to be about 1 meter wide, the size of a boulder, the gas drag would be so strong that the rock would spiral into the sun in less than a century. It seemed impossible to build a planet. The building blocks should all fall into the furnace before they could grow. But we are here. The Earth exists, so nature must have found a way to cross this barrier. The solution seems to lie in turbulence. The gas in the disk is not flowing smoothly. It is churning. There are eddies and whirlpools. There are pressure bumps. In these turbulent zones, the rocks can get trapped. They concentrate. Imagine a river with an eddy where driftwood collects. The pebbles in the solar nebula gathered in these streaming instabilities. They clustered together, and when enough pebbles gather in one place, something magical happens. The collective gravity of the swarm takes over. Suddenly, they are not just individual rocks held together by static electricity. They are a heavy cloud. They collapse under their own weight. They bypass the slow process of sticking together one by one. They jump straight from a swarm of pebbles to a solid object kilometers wide. A planetesimal is born. These planetesimals are the seeds of worlds. They are irregular, potato-shaped lumps of rock and metal, perhaps 10 to 100 kilometers across. They are large enough to have significant gravity. Now, the game changes. It is no longer about static electricity or gas drag. It is about gravity. It is about accretion. The planetesimal moves through the disk like a vacuum cleaner. Its gravity reaches out and grabs smaller rocks. It pulls them in. It clears its lane. This process starts to generate heat. When a rock falls onto the surface of a planetesimal, it hits with the force of a bomb. The kinetic energy of the fall is converted into thermal energy. The young world begins to warm up. It is being hammered into existence. But it is not just external impacts. There is heat coming from the inside, too. The dust that formed the Earth contained radioactive elements: aluminum-26, potassium-40, uranium. These are unstable atoms forged in supernovae. As they decay, they release energy. They release heat. In a small rock, this heat leaks out into space. But as the planetesimal grows, the rock itself acts as an insulator. The heat is trapped deep inside. The core begins to bake. The temperature climbs. Rock is a poor conductor of heat. The warmth accumulates. 500 degrees, 1,000 degrees. We are moving toward a critical moment, the moment of melting. But for now, the object is still a rubble pile. It is a loose collection of rocks and dust, holding together by gravity, but not yet fused into a single solid. It is porous. It is lumpy. Look around the solar system at this time. It is a chaotic shooting gallery. There are millions of these planetesimals. They are swarming around the sun. Inevitably, they collide. Some collisions are destructive. Two objects smash into each other at high speed and shatter back into dust. The process moves backward, but other collisions are constructive. They hit slow enough to merge. Two mountains become one bigger mountain. The gravity grows stronger. The feeding zone of the object expands. This is the period of oligarchic growth. A few large objects begin to dominate the disk. They eat the smaller ones. They become protoplanets. One of these protoplanets is the embryonic Earth. It is growing rapidly. It sweeps up the iron, the silicates, the magnesium. It is a hungry world. But it is dry. Remember the frost line. The Earth is forming in the hot zone. Any water that was in the dust has largely evaporated. The young Earth is a ball of dry, hot rock. The water will have to come later. It will have to be delivered. As the Earth grows to the size of Mars, the heat becomes overwhelming. The energy of the impacts and the radioactive decay is trapped. The temperature crosses the threshold. The rock begins to soften. The crystals lose their grip. The solid Earth turns into a thick, viscous fluid. The Earth melts. This is the Iron Catastrophe. It sounds violent, but it is a moment of ordering. In a liquid, things can move. Density determines destiny. The heavy stuff sinks. The light stuff floats. Iron and nickel are heavy. Droplets of molten metal begin to pool. They fall through the molten silicate rock like rain falling through the air. They stream downward toward the center of gravity. Billions of tons of molten iron rush to the center of the planet. They displace the lighter rock, which is forced upward. This vast reorganization releases even more heat. Gravitational potential energy turned into friction. The Earth glows like a star. It is a ball of magma shining in the dark. At the center, the iron collects. It forms a sphere. The core is born. This core will one day generate the magnetic field that protects our atmosphere. It is the dynamo of the world. But for now, it is just a hot, dense heart, buried under thousands of kilometers of molten rock. Above the core, the lighter elements, silicon, oxygen, aluminum, calcium, float. They form the mantle. And on the very top, the lightest scum of the magma ocean, the slag, begins to interact with the cold of space. The Earth at this stage is a terrifying, beautiful place. There is no land. There is no sea. There is only a global ocean of lava. The magma ocean, it churns. Convection currents bring hot material from the deep mantle to the surface. The lava bubbles and pops, releasing gases. This is the first atmosphere. Not the air we breathe today, but a primordial envelope of steam, carbon dioxide, and nitrogen, outgassed from the melting rocks. The sky is thick, heavy, and crushing. The sun, still young and faint, shines through this haze. It is a T-Tauri star now, prone to violent outbursts of X-rays and solar wind. The solar wind strips away the lighter gases, the hydrogen and helium, leaving behind the heavier molecules. The Earth is differentiating. It is separating into layers: core, mantle, atmosphere. It is becoming a planet, but it is not alone. The solar system is still crowded. There are other protoplanets roaming the disk. Orbits are crossing. Chaos is not done with the Earth yet. There is another world out there, a world the size of Mars. Astronomers call it Theia. It is on a collision course. But that is the story of the next chapter. For now, let us stay with the glowing, molten Earth. Imagine floating above it. It is a perfect sphere of red and orange light, turning slowly in the black vacuum. It radiates heat into the cold. It is cooling. The surface is starting to crust over. Patches of black rock appear on the lava ocean like ice flows on a river. They drift, collide, and sink again. These are the first attempts at a crust. The Earth is trying to build a skin. It is a time of fire and fluidity. The planet is liquid. It flows. It has no scars because every impact is swallowed by the melt. It is a blank slate, waiting for history to be written. The dust of the molecular cloud has traveled a long way. It has clumped, merged, heated, and melted. It has forgotten its shape as individual grains. It has become a unity. It has become a world. In the next chapter, we will witness the greatest violence in Earth's history. We will see the impact that nearly destroyed the world and instead created the moon. We will see the second melting. We will see the relationship between the Earth and its satellite begin. We will explore the tides of magma raised by the new moon. But for now, rest in the warmth of the accretion. Feel the gravity of the growing planet gathering you in. The dust has found its home. The wandering is over. The Earth is here. We have witnessed the gentle gathering of dust in the solar nebula. We have seen the electrostatic kiss that bound the first grains together. But the time of gentleness is over. As the planetesimals grow, they become heavy. They develop gravity, and gravity is a force that demands violence. The early solar system is no longer a quiet cloud. It is a shooting gallery, millions of rocks, ranging from the size of houses to the size of continents, are hurtling around the young sun at tens of thousands of kilometers per hour. Their orbits are chaotic, crossing and intersecting in a tangled web of potential collision. One of these rocks is the proto-Earth. It is not yet a planet. It is a planetary embryo, perhaps the size of Mars. It is growing by eating its neighbors. Every time a smaller rock passes nearby, the Earth's gravity snags it. The rock falls. But it does not fall like a stone dropping into a pond. It falls with the speed of a bullet. When it strikes the surface of the young Earth, the energy of motion, kinetic energy, is instantly converted into heat. Thermal energy. The rock vaporizes. The ground explodes. This process is called accretion. It is the violent assembly of a world. Each impact adds mass to the planet, increasing its gravity, which allows it to pull in even more rocks, which creates even more heat. It is a runaway feedback loop of growth and fire. But the heat does not just come from above. It comes from within. The dust that formed the Earth contained radioactive elements, unstable isotopes like aluminum-26, potassium-40, uranium-235. These atoms were forged in the heart of a supernova that exploded just before our solar system was born. They are ticking time bombs. As they decay, they release high-speed particles. These particles slam into the surrounding rock, creating friction on an atomic scale. They generate heat. In a small rock, this heat radiates away into space, but the Earth is getting big. Rock is an excellent insulator. The heat generated deep inside cannot escape. It is trapped. It builds up, degree by degree, century by century. The core of the planet begins to bake. The temperature climbs 500 degrees, 1,000 degrees, 1,500 degrees. The rock begins to glow a dull, angry red. The crystals that have held their shape for millions of years begin to vibrate. They lose their grip. Finally, the threshold is crossed. The rock melts. The solid earth becomes a liquid. And in a liquid, things can move. This triggers the most significant event in the geological history of our planet, the Iron Catastrophe. The early Earth was a homogeneous mixture, a jumble of rock and metal, thoroughly mixed like the ingredients of a cake. But rock, silicate, is lighter than metal, iron, and nickel. As long as the planet was solid, they were stuck together. But once it melted, gravity could sort them out. Imagine a glass of water and oil mixed together. If you let it sit, the oil floats and the water sinks. The same thing happened to the Earth, but with iron and rock. Billions of tons of molten iron, heavier than the surrounding stone, began to sink. It fell through the viscous magma like rain falling through honey. Great droplets of metal, kilometers wide, streamed downward toward the center of gravity. This was a landslide on a planetary scale. The falling iron released immense amounts of gravitational potential energy. As it fell, it rubbed against the rock, creating friction. This friction generated even more heat, enough to raise the temperature of the entire planet by 2,000 degrees. The Earth turned into a white-hot ball of magma. The entire planet melted. From the surface to the center, it was a roiling ocean of liquid fire. Attachment. The iron collected in the center. It formed a sphere of liquid metal thousands of kilometers wide. This is the core. It is the engine of the Earth. It is the dynamo. The lighter elements, silicon, oxygen, aluminum, magnesium, floated on top of the iron. They formed a thick shell of molten rock. This is the mantle. And on the very surface, the lightest scum of the magma ocean, the calcium, the sodium, the potassium, formed a thin, fragile skin. The crust. This process is called differentiation. It separated the Earth into layers. It gave the planet its structure. Without the Iron Catastrophe, Earth would be a uniform lump of rock. There would be no magnetic field. There would be no plate tectonics. There would be no life. Let us look at this young, differentiated Earth. It is a terrifying place. There is no land. There is no water. There is only lava, a global ocean of magma, churning and bubbling. Currents of hot rock rise from the deep mantle, cool slightly at the surface and sink back down. The surface is a patchwork of red fire and black crust. Rafts of solidified rock drift on the magma sea, colliding and sinking like ice flows in a river of hell. The atmosphere is thick and heavy. It is not air. It is rock vapor. The heat is so intense that rock itself evaporates. Above the magma ocean lies a cloud of gaseous silicate. As it cools high in the sky, it condenses. It rains liquid rock. Imagine a rainstorm where the droplets are made of molten lava. But the Earth is not alone in this chaos. The solar system is still rearranging itself. The giant planets, Jupiter and Saturn, are moving. This is the grand tack hypothesis. Jupiter formed first. It grew huge, sucking up the gas in the outer solar system. Then, it began to migrate inward. It spiraled toward the sun, plowing through the asteroid belt like a snowplow. Its massive gravity disrupted the orbits of the inner solar system. It scattered the planetesimals. It threw rocks into the sun, and it threw rocks out into the deep cold. It starved Mars, preventing it from growing larger. Then Saturn formed. Its gravity caught Jupiter and pulled it back. The two giants moved outward again, leaving behind a depleted, chaotic inner zone where the Earth was trying to survive. This migration cleared the deck. It removed much of the debris that would otherwise have pummeled the Earth forever. It stabilized the system, but it also delivered a gift. The Earth formed inside the frost line. It was too hot for water to exist as ice. The rocks that built the Earth were dry, enstatite chondrites. If the Earth had been built only from local materials, it would be a desert planet. No oceans, no life. But Jupiter's movement disturbed the outer asteroids, the carbonaceous chondrites. These rocks were born in the cold. They were full of water ice. Jupiter flung these wet rocks inward. They rained down on the molten Earth. They delivered the water. They delivered the volatile gases, carbon, nitrogen, sulfur. The ingredients of the atmosphere and the oceans arrived on the backs of asteroids, thrown by the gravity of a wandering giant. The water boiled instantly upon impact, turning to steam. The atmosphere became a high-pressure steam bath. The pressure was hundreds of times higher than it is today. Under this crushing blanket of steam, the magma ocean took longer to cool. The greenhouse effect was runaway. The heat was trapped. The Earth remained molten for millions of years. But slowly, the bombardment slowed. The planetesimals were used up. The solar system began to empty out. The Earth was left alone to cool. The surface temperature dropped. 2,000 degrees, 1,500 degrees, 1,000 degrees. At around 1,200 degrees, the first crystals began to form in the magma ocean. Olivine, a green mineral. It is heavy, so it sank. Then pyroxene. Then feldspar. A thin, black crust began to harden over the liquid interior. It was basalt, the same rock that comes out of volcanoes in Hawaii today. It was brittle and unstable. It was constantly being broken by meteorites and torn apart by the tides of magma below. But it was the beginning of permanence. The Earth was trying to build a skin. And then, just as the world was starting to solidify, the greatest catastrophe of all occurred. We are about 50 million years after the formation of the solar system. The Earth is a young, hot planet with a thin crust, but it shares its orbit. There is another planet nearby, a world the size of Mars. Astronomers call it Theia. It formed at a Lagrange point, a stable gravitational eddy just ahead or behind the Earth. For millions of years, Theia drifted peacefully, but as it grew, its orbit became unstable. It began to wobble. It drifted closer and closer to Earth, until one day the paths crossed. The collision was slow, but devastating. Theia slammed into the Earth at an oblique angle. It didn't hit head-on, it was a glancing blow. But the energy released was enough to melt the entire planet all over again. The shock wave traveled through the Earth, liquefying the mantle. Theia was destroyed. Its iron core plunged through the Earth's mantle and merged with the Earth's core. The heart of the invader became part of the host. But the outer layers of Theia and a huge chunk of the Earth's own crust and mantle were blasted into space. Billions of tons of molten rock were sprayed into orbit. For a few thousand years, the Earth had a ring. It looked like Saturn, but the rings were made of lava, not ice. They glowed red in the night sky. Gravity worked on this ring. The debris clumped together. It snowballed. Within just a century, an instant in geological time, the debris coalesced into a single sphere. The moon was born. This new moon was much closer than the one we see today. It was only 20,000 kilometers away. It loomed huge in the sky, 20 times larger than the modern moon. It orbited the Earth once every few hours. The tides it raised on the molten Earth were monstrous. Waves of magma, kilometers high, rushed across the surface of the planet, following the moon. The friction of these tides kept the Earth hot. It prevented the crust from freezing. But the moon was also moving away. It was stealing angular momentum from the Earth. As it drifted outward, the tides grew weaker. The Earth began to slow its spin. The day lengthened from 6 hours to 10, to 12, to 24. With the moon receding, the Earth could finally cool. The magma ocean began to freeze in earnest. The crust thickened. The steam atmosphere began to condense. Clouds formed, not clouds of rock, but clouds of water. The first rain began to fall, but the ground was still too hot. As the rain hit the surface, it hissed and boiled back into steam. It was a cycle of rain out and boil off, a planetary sauna. Eventually, the rock cooled below 100 degrees Celsius. The water could stay liquid. It pooled in the low places. It filled the impact craters. It filled the basins. The deluge began. It rained for thousands of years. A continuous torrential storm that washed the atmosphere clean of carbon and dust. The sky turned from black to gray to blue. The first oceans were born. They were not like our oceans. They were hot, perhaps 60 or 80 degrees Celsius. They were acidic, filled with carbonic acid from the sky. And they were green, rich in dissolved iron. But they were water, the solvent of life. The stage was set. The Earth was now a water world, a global ocean covering almost the entire surface, punctuated only by the peaks of massive volcanoes poking through the waves. There were no continents yet, just chains of black islands in a green sea, under a faint orange sun. In the next chapter, we will explore this ocean. We will look at the chemistry of the early water. We will see how the first continents, the cratons, began to form from a new kind of rock, granite. we will see the beginning of plate tectonics, the skin of the Earth beginning to slide, subduct, and recycle itself. And we will look for the spark, the chemical accident that happened in the deep, hot vents of this primordial sea, the accident that led to us. But for now, hover over the magma ocean as it cools. Watch the first black rafts of crust forming on the red fire. Watch the steam clouds gathering. Feel the heat radiating into space. The planet is quieting down. The violence of accretion is over. The long, slow stability of geology is about to begin. Rest in the cooling dark. The fire is banking. The world is preparing for its future. The violence of the collision that created the moon has faded. The debris has cleared from the sky. The Earth is left alone in the darkness, a spinning sphere of glowing red magma. It is a wounded world, cauterized by fire. But now, the long healing begins. The era of heat gives way to the era of cooling. Thermodynamics is the ruler of this age. The Earth is radiating its heat out into the cold vacuum of space. It is bleeding energy. As the temperature drops, the physics of the surface begins to change. The liquid rock, which has churned and roiled for millions of years, begins to stiffen. At 1200 degrees Celsius, the first crystals appear. They are tiny, geometric structures of olivine and pyroxene. They float in the melt like ice crystals forming on a winter pond. But these crystals are heavy. In the calm eddies of the magma ocean, they sink. They rain down into the depths, leaving the lighter liquid behind. This remaining liquid, rich in silica and feldspar, cools further. It becomes viscous. It turns black. A thin, fragile skin begins to form over the surface of the planet. It is a crust, but it is not the solid ground we know today. It is a raft. Imagine a frozen lake where the ice is constantly breaking, shifting, and diving back into the dark water. That is the crust of the Hadean Earth. Plates of black basalt, miles wide, drift on the sea of fire. They collide. They subduct. They melt again. The Earth is trying to build a shell, but the heat from below keeps breaking it. But the cooling is relentless. The rafts grow larger. They grow thicker. The red glow of the lava is slowly covered by the black mask of the rock. The light of the planet dims. If you were watching from space, you would see the Earth turn from a star-like object into a dark, solid shadow. But the Earth is not naked. It is wrapped in a blanket. During the meltdown, the rock released vast amounts of gas, volatiles, water vapor, carbon dioxide, nitrogen, sulfur, methane. These gases formed a dense, crushing atmosphere. The air pressure on the surface is immense, perhaps 20 times, maybe even 100 times higher than it is today. It is a heavy, suffocating weight. The sky is not blue. It is a hazy, reddish-brown fog, choked with clouds of rock dust and sulfur. It is a greenhouse of terrifying efficiency. This atmosphere traps the heat. It slows the cooling, but it also holds the key to the next transformation: water. The atmosphere is saturated with steam, trillions of tons of water, delivered by the comets and outgassed from the mantle, are hanging in the sky as vapor. They want to fall. They want to become rain. But the surface is too hot. Every time a raindrop forms high in the atmosphere and falls, it hits the layer of superheated air near the ground and flashes back into steam. It is a virga rain, rain that never touches the ground. The sky is weeping, but the earth is dry. But the temperature continues to drop. 500 degrees, 300 degrees, 200 degrees. Finally, a threshold is crossed. The ground cools below the boiling point of water, which, at this high pressure, is much higher than 100 degrees Celsius. The first drop hits the rock. It hisses. It dances on the hot stone, evaporating quickly. But then comes another and another. The rock cools under the assault. The water begins to pool. The deluge begins. It rains. It rains with a violence that has no modern equivalent. It rains not for days or weeks, but for centuries, perhaps for thousands of years without stopping. The sky unloads the ocean it has been holding. Great rivers of hot water rush over the black basalt plains. They flash flood the impact craters. They carve deep canyons into the fresh rock. The water is scalding hot, but it is liquid. It collects in the lowlands. The basins fill. The magma ocean is replaced by a water ocean. But this is not the blue ocean of a vacation postcard. It is an alien sea. The water is hot, perhaps 80 or 90 degrees Celsius. It is a global spa bath. And it is not blue. It is green. Olive green. Why green? Because the water is rich in dissolved iron. There is no oxygen in the atmosphere to rust the iron and turn it red. In the anoxic environment of the early Earth, iron dissolves easily in water. The ocean is a chemical solution of ferrous metal. It is also salty, but much saltier than today, and it is acidic. The atmosphere is full of carbon dioxide. When CO2 mixes with water, it forms carbonic acid, and the rain that fell for 1,000 years was acid rain. This acid rain attacked the rocks. It dissolved them. It stripped the magnesium, the calcium, and the salt from the crust and washed them into the sea. The chemical weathering of the planet was accelerating. The ocean was becoming a mineral soup. And the sky cleared. As the water vapor turned to rain, the clouds thinned. The heavy blanket was removed. The pressure dropped. For the first time, sunlight could reach the surface of the ocean. The sun that shone on this green sea was different. It was the faint young sun. It was smaller and cooler than today, shining with only 70% of its current brightness. Under a modern atmosphere, this weak sun would not be enough to keep the Earth warm. The oceans would have frozen into a solid block of ice. This is the faint young sun paradox. Why didn't the Earth freeze? The answer lies in the remaining blanket, the carbon dioxide. Even though the steam was gone, the atmosphere was still thick with CO2. This greenhouse gas trapped the meager heat of the young sun, keeping the oceans liquid. It was a perfect balance. A dim star, but a thick blanket. So now we have a water world. The Earth is covered in a global ocean miles deep. There are no continents, no Africa, no Asia, no Americas. Just an endless expanse of green waves under an orange sky. But the Earth is restless. The crust beneath the ocean is not stable. It is still thin, hot basalt, and the mantle below is churning. Volcanoes pierce the surface of the water. Massive shield volcanoes like Hawaii, but larger, rise from the seafloor. They form chains of black islands. This is the only dry land on Earth, scattered archipelagos of smoking rock. These islands are temporary. The rain erodes them. The waves batter them. They sink back into the sea. The Earth cannot yet sustain a continent. Basalt is too heavy. When it piles up, it sinks into the soft mantle. It cannot float high enough to make dry land that lasts. To make a continent, the Earth needs a new material. It needs a rock that is lighter, stronger, and more buoyant than basalt. It needs granite. Granite does not come from the mantle. It has to be made. It is a cooked rock. It is the product of distillation. The process begins with subduction. The crust of the Earth is broken into plates. One plate of basalt dives beneath another, sinking back into the hot mantle. But this basalt is wet. It has been soaking in the ocean for millions of years. As the wet rock dives into the heat, the water is squeezed out. The water mixes with the hot rock of the mantle. As we learned in the volcano story, water lowers the melting point of rock. It acts as a flux. This creates a new kind of magma. It is rich in silica. It is rich in quartz. It is lighter than the basalt around it. It rises. This new magma erupts or cools underground to form granite. Granite is a low-density rock. It is a cork. When it forms, it floats on top of the heavy mantle. It cannot sink. Slowly, over hundreds of millions of years, these blobs of granite begin to accumulate. They gather together. They resist subduction. When two granite islands crash into each other, they don't dive. They crumple. They rise up. They build mountains. These are the cratons, the ancient cores of the continents, the seeds of the land. We can still find these cratons today. They are the oldest rocks on Earth. The Pilbara Craton in Australia, the Kapval Craton in South Africa, the Canadian Shield. When you stand on the smooth, pink granite of the Canadian wilderness, you are standing on the solidified foam of the Archean Ocean. You are standing on the first land that refused to sink. How do we know this story? How do we know about the water world and the cool early Earth? The rocks from that time have been destroyed, melted, and eroded. The history book has been burned. But there are tiny survivors, microscopic time capsules, crystals called zircons. Zircons are the toughest mineral on Earth. They are harder than steel. They are chemically inert. They do not melt until extreme temperatures. When a granite rock forms, tiny grains of zircon crystallize inside it. And once a zircon forms, it is forever. Even if the rock around it erodes, even if the mountain is ground to sand, the zircon survives. It gets washed into a river, buried in sediment, baked into new rock, and pushed up again. It is a witness. In the Jack Hills of Western Australia, scientists found zircons that are 4.4 billion years old. They formed just after the birth of the Earth. When they analyzed the chemistry of these crystals, specifically the oxygen trapped inside them, they found something shocking. The oxygen signature showed that the crystal had grown in the presence of liquid water. Cool, liquid water. This rewrote the history of the Earth. It meant that the Hadean era, the hellish time of magma, ended much faster than we thought. The Earth cooled quickly. The oceans formed early. Within just 100 million years of its birth, the Earth was a blue, watery world. It was ready for life almost immediately. So, picture the Archean Earth now. It is 3.5 billion years ago. Small continents of gray granite are rising out of the green sea. They are barren. There is no moss, no grass, just naked rock weathered by the wind and the acid rain. The coastlines are jagged and rough. The tides are massive. Because the moon is still close, the water rushes in and out with terrifying speed, scrubbing the land every few hours. This creates vast tidal flats, shallow, warm pools of water that are wet, then dry, then wet again. These tidal pools are chemical laboratories. As the water evaporates, the chemicals concentrate. They get thick, they form a brine, but the real action might be happening deeper. Let us dive into the green ocean, down past the reach of the faint sun, down to the crushing dark of the seafloor. The crust here is cracked. The tectonic plates are pulling apart. water seeps down into the cracks. It touches the hot magma beneath. It heats up to 400 degrees Celsius, dissolving minerals from the rock. Then it shoots back up. It blasts out of the seafloor as a jet of superheated mineral-rich fluid. As this hot fluid hits the cold ocean water, the minerals precipitate instantly. They form chimneys, black chimneys of sulfide rock towering tens of meters high, black smokers, or in cooler areas, white smokers. These vents spew alkaline fluids. They build strange, porous towers of limestone. They look like honeycombs. Inside the microscopic pores of these white smokers, a gradient exists. The ocean water is acidic. The vent water is alkaline. This difference creates a natural battery, a flow of energy. Carbon, hydrogen, and nitrogen collect in these pores. They are trapped. They are pushed together by the heat and the chemical flow. They begin to organize. This is the probable birthplace of life, the hydrothermal vent hypothesis. The Earth is no longer just a rock physics experiment. It is becoming a chemistry experiment. The ingredients are all there. The energy is there. The solvent, water, is there. The planet is pregnant. It is waiting for the spark. But the surface is still dangerous. The ultraviolet radiation from the sun is lethal. There is no ozone layer yet. If you stood on one of the granite islands, you would burn in minutes. The DNA of any life form would be shattered. That is why life, when it starts, must start in the deep, or in the mud, or under a rock. It must hide from the light that feeds it. The atmosphere is also evolving. The volcanoes are still erupting, pumping out gases, but the chemistry is changing. Methane, a powerful greenhouse gas, is building up. It creates a haze, an orange smog that wraps the planet like the atmosphere of Titan, the moon of Saturn. This haze protects the surface slightly, but it also traps heat. The Earth is a steam engine, a chemical vat, a geology lab. It is a system seeking equilibrium, but never finding it. And through it all, the water cycles, evaporation, condensation, precipitation. The river flows to the sea. The sea circulates. The water interacts with the rock. This interaction, the carbon-silicate cycle, begins to regulate the SU, temperature. If the Earth gets too hot, it rains more. The rain weathers the rock, scrubbing CO2 out of the air. The greenhouse effect weakens. The Earth cools. If the Earth gets too cold, it stops raining. The volcanoes keep pumping CO2, but the rocks don't scrub it out. The greenhouse effect strengthens. The Earth warms. The planet has developed a thermostat, a self-correcting mechanism that keeps the temperature within the narrow range where water can remain liquid. This thermostat has held for 4 billion years. It is the reason we are here. Mars had water once, but its thermostat broke. It froze. Venus had water once, but its thermostat broke. It boiled. Earth stayed in the middle, the Goldilocks planet. In the next chapter, we will see the result of this stability. We will see the rise of the single cell. We will explore the 3 billion years where slime ruled the world, the slime world. We will see how bacteria invented the technology of photosynthesis and how they changed the color of the sky from orange to blue. We will see the great oxygenation event, the catastrophe that poisoned the world and froze it solid, only to pave the way for complex life. But for now, rest in the sound of the first ocean. Imagine the waves, green and heavy, crashing against a shore of black volcanic glass. There are no birds to sing, no trees to rustle, just the wind and the water. It is a lonely sound, but it is the sound of home. The water is preparing the way. The cradle is being rocked by the moon. Drift on the surface of the global sea. You are floating in the potential of the past. We have watched the universe build itself from a single point of infinite heat into a majestic clockwork of galaxies and stars. We have seen the Earth coalesce from the dust of the solar nebula, a molten ball cooling in the vacuum. Now, we hover above this young world. It is 4 billion years ago. If you looked out the window of a spacecraft at the Archean Earth, you would not recognize it as home. It is an alien planet. The sky is not blue. It is a hazy, toxic orange, rich in methane and carbon dioxide. The oceans are not blue. They are olive green, saturated with dissolved iron. The continents are stark, barren rock, black and gray, with no hint of green. There is no sound but the wind and the waves. It is a silent, waiting world. But deep beneath the surface of those iron-rich seas, something is happening. A threshold is being crossed. The universe is about to perform its greatest trick. It is about to wake up. It is about to transition from dead chemistry to living biology. We do not know exactly where it happened. It might have been in a shallow sun-warmed tidal pool, where molecules were concentrated by evaporation. Or, more likely, it was in the crushing dark of the deep ocean, along the ridges of hydrothermal vents. These vents act as chemical chimneys. They spew mineral-rich, superheated water from the Earth's crust into the cold ocean. The contrast between the hot, alkaline fluid and the cool, acidic seawater creates a chemical gradient, a natural battery. Energy is flowing. In the microscopic pores of the rock chimneys, complex molecules begin to gather. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the Schnaps elements forged in the stars, begin to link up. They form chains, amino acids, nucleotides, lipids. For millions of years, this chemical soup churns. It is a game of trial and error played by trillions of molecules over eons. And then, one day, a specific arrangement forms, a molecule that can do something new. It can copy itself. This is the moment of abiogenesis, life from non-life. The molecule copies itself, but imperfectly. The errors are mutations. Some copies are better at surviving than others. Evolution begins. Soon, these replicating molecules become trapped inside tiny bubbles of fat, lipids. This is the first cell, the first membrane. It separates self from world. Inside the bubble, the chemistry is protected. Outside, the ocean rages. This first life form, we call it Luca, the last universal common ancestor, is microscopic, simple, and fragile. It eats the chemical soup of the vents. It lives in the dark, but it is alive. It has agency. It wants to persist. Rate 100%, pitch 1%. For 1 billion years, life remains small. It is a slime world. Bacteria and archaea dominate the planet. They cling to rocks. They float in the water. They are anaerobic. They do not need oxygen. In fact, oxygen is a poison to them. But evolution is restless. It is always looking for a better energy source. The chemical soup of the vents is limited. But up above, beyond the surface of the water, there is a virtually infinite source of power: the sun. About 2.5 billion years ago, a specific type of bacteria, cyanobacteria, stumbles upon a new technology. It develops a pigment, chlorophyll. This pigment allows the cell to drink sunlight. It allows it to split water molecules to get electrons. As we explored in the story of light, this process releases a waste product, a gas, oxygen. At first, the oxygen is absorbed by the ocean. It reacts with the dissolved iron. The green oceans turn red as the iron rusts and falls to the seafloor. This rust forms the banded iron formations we mine today. The steel in your car was laid down by bacteria billions of years ago. But eventually, the iron runs out. The ocean cannot hold any more oxygen. The gas bubbles up. It breaks the surface. It enters the atmosphere. This leads to the first global catastrophe, the Great Oxygenation Event. To the anaerobic life that ruled the Earth, oxygen was a toxic sludge. It burned them. It destroyed their cellular machinery. As the oxygen levels rose, it triggered a mass extinction of microbial life. 99% of life on Earth may have died. It was a holocaust caused by the invention of breathing. The catastrophe worsened. The methane in the atmosphere, which had acted as a greenhouse gas keeping the Earth warm, reacted with the oxygen and turned into carbon dioxide and water. The greenhouse blanket was stripped away. The temperature plummeted. The Earth froze. Ice sheets spread from the poles all the way to the equator. The entire planet became a white, frozen ball hurtling through space. This was the snowball Earth, or the Huronian glaciation. For hundreds of millions of years, the Earth was locked in ice. The life that survived huddled near the volcanic vents, or in thin pockets of water beneath the glaciers. It seemed like the experiment of life had failed. The cyanobacteria had been too successful. They had frozen their own world. But the Earth is geologically alive. Volcanoes continued to erupt beneath the ice. They pumped carbon dioxide back into the atmosphere. Because the ice covered the rocks could not absorb the CO2. It built up. Rate 100%, pitch 1%. Slowly, the greenhouse effect returned. The heat built up, and then the thaw began. The ice cracked. The oceans opened. Life emerged from the freeze into a new world, a world with an oxygen-rich atmosphere and a blue sky. The survivors of the oxygen crisis had adapted. They had learned a new trick, aerobic respiration. Instead of fearing oxygen, they learned to use it. They learned to burn their food with it. Using oxygen to burn sugar releases 18 times more energy than the old anaerobic methods. It was like switching from a candle to a jet engine. This surge in available energy allowed life to grow bigger. It allowed for complexity. And then another miracle occurred. The most important merger in history, endosymbiosis. Imagine a large, predatory single-celled organism. It swims through the ocean, eating smaller bacteria. One day, it engulfs a small, energy-efficient bacteria that knows how to use oxygen. Usually, the predator would digest the prey. But this time, something different happens. The small bacteria survives inside the large one. It strikes a deal. "I will make energy for you," it says, "if you protect me and give me food." The predator agrees. The two become one. The small internal bacteria evolves into the mitochondria, the powerhouse of the cell. Every cell in your body today is the descendant of this ancient merger. You are a colony of colonies. Later, some of these new complex cells swallowed a cyanobacterium, the photosynthesizer. This became the chloroplast. This lineage became the plants. This new type of cell, the eukaryote, was larger, more complex, and packed with energy. It had a nucleus to protect its DNA. It had internal factories. It was ready to build. For a long time, a period scientists call the boring billion, these eukaryotes lived quietly. They evolved sex, mixing their genes to create variation. They drifted in the oceans. But eventually, They learned to cooperate. Single cells began to stick together. They formed colonies. At first, every cell in the colony was the same, but then they began to specialize. "I will handle the movement," said the outer cells. "I will handle the digestion," said the inner cells. "I will handle the reproduction," said the germ cells. True multicellular life was born. The first animals appeared. They were simple, soft-bodied creatures, sponges, jellyfish, fronds that looked like ferns but lived in the dark depths, the Ediacaran biota. They had no eyes, no teeth, no hard shells. It was a garden of Eden, a peaceful world of filter, feeders drifting in the slow currents. But the peace would not last. The energy was too high. The potential for competition was too great. About 540 million years ago, the Cambrian explosion occurred. In a geological blink of an eye, all the major body plans of animals appeared. Eyes evolved. Suddenly, the predator could see the prey. Armor evolved. Hard shells, spikes, and claws. The arms race began. The ocean filled with trilobites, worms, and strange alien creatures like Anomalocaris, a meter-long predator with grasping claws. The biological information explosion matched the Big Bang in its intensity. Life was diversifying into every niche, but the land was still barren. It was a world of rock and sand, perhaps covered in a thin slime of algae, but no trees, no grass, no animals. The continents were empty. The next great journey was the invasion of the land. The plants went first. Algae crept up the shorelines, adapting to the harsh, dry air. They evolved into mosses, then ferns. They developed waxy skins to hold in their water. They developed roots to mine the rock for minerals, turning stone into soil. They terraformed the continents. They pumped even more oxygen into the air. They created the ozone layer, a shield of gas that blocked the deadly ultraviolet radiation of the sun. Before ozone, the land was sterilized by the sun. Now it was safe. In the shadow of these first forests, the animals followed. Insects were likely the pioneers. Scorpions and millipedes scurrying out of the water to eat the rotting vegetation. Because the oxygen levels were so high, they grew huge. Dragonflies with the wingspans of eagles, millipedes as long as cars. Then came the fish. A specific lineage of fish, the lobe-finned fish, lived in shallow, swampy waters. They had strong, fleshy fins that they used to push themselves through the mud. Over millions of years, these fins evolved into legs. The swim bladder, used for buoyancy, evolved into lungs. One day, a creature, perhaps Tiktaalik, pulled itself out of the water and onto the muddy bank. It looked around with eyes adapted for water, breathing air with difficulty. It was not staying. It probably went back in. But the threshold had been crossed. The amphibians had arrived. They were tethered to the water. They needed it to lay their eggs, but they could walk on the earth. They were followed by the reptiles, who developed a revolutionary technology, the amniotic egg, a waterproof shell that carried its own private ocean inside. With this egg, animals could leave the water behind completely. They could march into the deserts. They could conquer the interior of the continents. The age of reptiles began. The dinosaurs rose, dominating the planet for 150 million years. They were magnificent, diverse, and successful. They filled every niche, from the size of a chicken to the size of a building. But the universe is violent. We know how their story ended. A rock from the sky, A remnant of the solar system's chaotic birth slammed into the Yucatan. The winter returned. The giants fell. But in the ashes of that catastrophe, a small, furry creature crawled out of its burrow. A mammal, our ancestor. The mammals had been living in the shadows of the dinosaurs for millions of years, staying small, nocturnal, and terrified. But with the tyrants gone, the world was open. They radiated outward. They grew large. They returned to the sea as whales. They took to the skies as bats. And one lineage took to the trees. The primates. They developed grasping hands to hold branches. They developed forward-facing eyes to judge distances for jumping. They developed large brains to navigate the complex social politics of the troop. And then, the climate changed again. The forests of Africa dried up. The trees receded, leaving wide bands of open savanna grass. One ape was forced to come down from the trees. To see over the tall grass, it stood up on its hind legs. It became bipedal. This freed its hands. It could now carry things. Food, tools, babies, fire. This brings us to the edge of the human story. But before we look at ourselves, we must pause and look at the planet itself. The Earth of today is unrecognizable from the Hadean hellscape we started with. It is a blue jewel, wrapped in white clouds, covered in green velvet. It is a living organism. The Gaia hypothesis suggests that life interacts with the inorganic surroundings to form a synergistic, self-regulating system. The plankton in the ocean produce clouds. The forests regulate the rainfall. The weathering of rocks regulates the temperature. Life does not just exist on the rock. Life is the rock. The limestone cliffs of Dover are made of the skeletons of trillions of microscopic creatures. The oil we burn is the compressed bodies of ancient algae. The oxygen we breathe is the exhalation of the biosphere. The Earth is a biological construct as much as a geological one. From the first second of the Big Bang, to the formation of the first atom, to the first star, to the first cell, to the first thought, it is an unbroken chain. Complexity has been increasing steadily, fighting the tide of entropy. The universe has been waking up, step by step. Matter learned to organize, then it learned to replicate, then it learned to sense, then it learned to think. In the next chapter, we will explore the final leap, the leap from biology to consciousness. We will look at the human mind, the most complex object in the known universe. We will look at how a collection of neurons, made of the same atoms as the stars, can wake up and ask the question, where did I come from? We will see the birth of language, art, and science. We will see how the universe, through us, has finally developed the ability to tell its own story. For now, drift over the green earth. See the herds of animals migrating across the plains. See the whales breaching in the oceans. See the lights of the cities beginning to flick on as the sun sets. You are the product of 4 billion years of struggle, luck, and evolution. You are the leading edge of the wave. Rest in the knowledge that you belong here. You are the universe coming to know itself. The earth has cooled. The magma ocean has frozen into a solid crust. The water ocean has rained down from the sky. But the planet is not finished. It is merely the end of the beginning. For billions of years, the earth was a restless child, trying to decide what shape it wanted to be. Now, it enters its adolescence. We have seen the first continents, the cratons, floating like rafts on the mantle, but they were small, isolated. They were islands in a global sea. To build the world we know today, these islands had to move. They had to collide. They had to merge. This is the story of plate tectonics. It is the engine that drives the surface of the Earth. It is a recycling system on a planetary scale. The crust of the Earth is not a single, unbroken shell like an egg. It is cracked. It is broken into puzzle pieces called tectonic plates. These plates float on the hot, soft rock of the mantle below. And because the mantle is churning, convecting heat from the core to the surface, the plates ride these currents like leaves on a river. In the early Earth, the mantle was hotter. The currents were faster. The plates moved with a frantic speed. But as the planet cooled, the engine slowed down. The plates grew thicker and heavier. They began to grind against each other with immense force. When two plates meet, one of three things happens. They can slide past each other, creating earthquakes. They can pull apart, creating new ocean floor. Or they can crash head-on. When an oceanic plate, made of heavy, dense basalt, crashes into a continental plate, made of light, buoyant granite, the heavy plate loses. It dives. It sinks beneath the continent and plunges back into the mantle. This is subduction. It is the most important geological process on Earth. It is the garbage disposal of the crust. It takes the old, cold rock of the ocean floor and recycles it back into the deep Earth. Attachment, zuo, attachment. As the plate sinks, it carries water with it. As we learned in the volcano story, this water lowers the melting point of the rock. It creates magma. This magma rises up through the continent above, erupting as a chain of volcanoes. The Andes, the Cascades, the Ring of Fire. These are the scars of subduction. But what happens when two continents crash? Granite is too light to sink. It refuses to subduct. So, when two continents collide, they buckle, they fold, they rise up, they build mountains. The Himalayas are the result of India crashing into Asia. The Alps are Africa crashing into Europe. The Appalachians are the ghost of an ancient collision that happened hundreds of millions of years ago. About 1 billion years ago, this process reached a climax. All the scattered cratons, all the islands of granite were swept together by the currents of the mantle. They met in a single location. They formed a supercontinent. We call it Rodinia. Imagine a world with only one continent, a vast, barren landmass sitting on the equator. The interior of Rodinia was a desert, thousands of miles from the sea. It was lifeless rock, scoured by wind and rain. The coastlines were rugged, battered by the waves of a single global ocean called Merovia. Rodinia lasted for millions of years. But the Earth is restless. The heat builds up beneath a supercontinent. The thick crust acts as a blanket, trapping the mantle heat. Eventually, the pressure becomes too great. The continent began to rift. It tore apart. Huge cracks opened in the ground, spewing lava. The pieces of Rodinia drifted away from each other, opening new oceans between them. This breakup had a profound effect on the climate. As the new oceans opened, they created more coastline. More coastline meant more rain. More rain meant more weathering. Rain dissolves rock. As it does, it pulls carbon dioxide out of the atmosphere. This is the silicate weathering thermostat. The breakup of Rodinia accelerated this weathering. It scrubbed the CO2 from the sky. The greenhouse effect collapsed. The Earth began to cool. It cooled so much that the ice caps at the poles began to grow. White ice reflects sunlight back into space. This cools the planet further, which makes the ice grow more. It is a runaway feedback loop. The ice albedo feedback. The ice marched from the poles to the equator. It covered the continents. It covered the oceans. The entire planet became a white ball. This was the cryogenian period, the second snowball Earth. For millions of years, the Earth was a frozen wasteland. The oceans were sealed under a kilometer of ice. The only life that survived huddled around the volcanic vents in the deep sea or in tiny pockets of meltwater on the surface. It seemed like the end, but the volcanoes saved us again. Beneath the ice, the volcanoes continued to erupt. They pumped carbon dioxide into the atmosphere. But because the rocks were covered in ice, the weathering stopped. The CO2 could not be scrubbed out. It built up. The atmosphere became thick with greenhouse gas. The heat began to rise. Finally, it was enough to melt the ice at the equator. The feedback loop reversed. The dark ocean absorbed the sun. The ice retreated. The world thawed. But the world that emerged from the ice was different. The chemistry of the ocean had changed. The glaciers had ground the continents into dust, dumping massive amounts of nutrients, phosphorus, iron, into the sea. The algae bloomed. They produced oxygen. The oxygen levels spiked. This surge of oxygen, combined with the nutrient-rich waters, triggered an explosion of life. The Ediacaran biota appeared. Strange, soft-bodied creatures, fronds and discs, drifting in the shallow seas. They were the first experiments in complex, multicellular life. The Earth was getting ready for the Cambrian explosion. But before we get to the animals, we must look at the time in between. The boring billion, between the Great Oxygenation Event, 2.4 billion years ago, and the breakup of Rodinia, 800 million years ago, there was a long period where not much happened. The oxygen levels were low but stable. The climate was mild. The continents were drifting slowly. Life was mostly slime. Scientists call this the boring billion, but it was actually a time of crucial preparation. Inside the cells, the machinery of complexity was being refined. The eukaryotes, the cells with nuclei, were learning to have sex. This sounds simple, but sexual reproduction is the engine of evolution. It shuffles the genes. It creates variety. It allows life to adapt faster. They were also learning to die. Programmed cell death. Apoptosis. For a single-celled organism, death is the enemy. But for a multicellular organism, death is a tool. To build a hand, the cells between the fingers must die. To build a brain, the excess neurons must be pruned. The invention of death allowed for the invention of the body. So, while the surface of the Earth looked quiet, the biology was humming. The software was being written. Then came the chaos of the cryogenian, the freeze, the thaw, the nutrient dump, and suddenly the software was ready to run. The first shells appeared, small, shelly fossils. Life learned to build armor from the minerals in the water, calcium carbonate, silica. This changed the geology of the planet again. When these shelled creatures died, their shells sank to the bottom. They formed layers of limestone. They locked carbon away in the rock. Life was no longer just living on the rock. It was making the rock. The biosphere and the geosphere had merged completely. This brings us to the Phanerozoic Eon, the eon of visible life, the last 540 million years. This is the chapter we know best: the trilobites, the fish, the dinosaurs, the mammals. But it is important to remember that this era is just the frosting on the cake. The vast majority of Earth's history nearly 90% happened before the first animal crawled out of the mud. The Precambrian was the time of foundation. It was the time when the air was made, the water was poured, and the land was built. As we look at the continents today, we see the puzzle pieces of the past. South America fits perfectly into Africa. North America fits into Europe. If you close the Atlantic Ocean, the Appalachian Mountains connect directly to the Caledonian Mountains in Scotland. They are the same mountain range, torn in half by the drift. We are living on a moving puzzle. The Atlantic is getting wider by a few centimeters every year, about the speed your fingernails grow. The Pacific is shrinking. In the future, the continents will come together again. A new supercontinent will form, Pangaea Proxima. The cycle of Rodinia and Pangaea will repeat. The Earth breathes in continents and exhales them. This movement also drives the deep carbon cycle. It regulates the temperature. It keeps the planet habitable. Without plate tectonics, Earth would be dead. Mars is dead because it is too small. Its core cooled. Its tectonics stopped. It couldn't recycle its crust. Venus is dead because it is too hot. Its crust is soft and plastic. It cannot break into plates. It has stagnant lid tectonics. The heat builds up until the whole planet melts in a catastrophic resurfacing event. Earth is just right. The Goldilocks planet. The plates move just fast enough to recycle the nutrients and the carbon, but slow enough to provide a stable platform for life. But this stability is not guaranteed. It depends on the internal heat of the planet. And as we know, that heat is fading. One day, billions of years from now, the engine will stop. The plates will freeze. The volcanoes will die. The Earth will become a static monument to its former glory. But that is a story for the deep future. For now, the Earth is vibrant. It is shifting under our feet. In the next and final chapter, we will look at the atmosphere again. We will see how the delicate balance of gases has been maintained for 4 billion years. We will look at the ozone layer, the shield that allowed life to leave the water. We will look at the role of plants in terraforming the continents. We will see how the Earth became a self-regulating system, a living planet. For now, imagine the continents drifting slowly through the dark ocean of time, colliding, merging, breaking apart. It is a slow dance, a waltz of granite and basalt. You are riding on one of these rafts. You are safe. The ground is solid for now. Rest in the deep time of geology. We have watched the Earth grow from a cloud of dust into a molten ball, cool into a water world, and freeze into a snowball. We have seen the continents drift and the life emerge from the vents. But the story of the early Earth is not just about rock and water. It is about the air. It is about the thin blue line that separates the living planet from the cold void. The atmosphere we breathe today is a biological artifact. It is not the atmosphere the Earth was born with. The original air, the hydrogen and helium captured from the solar nebula, was stripped away by the solar wind. The second atmosphere, the steam and carbon dioxide belched by volcanoes, was toxic and hot. To create the modern sky, a third transformation was needed. It required a partnership between the geology and the biology. Let us look at nitrogen. It makes up 78% of every breath you take. It is inert, stable, and unreactive. Where did it come from? It came from the deep interior. Nitrogen was trapped in the mantle rocks. As the volcanoes erupted over billions of years, they released nitrogen gas. But unlike carbon dioxide, which dissolves in the ocean or is eaten by plants, nitrogen stays in the air. It accumulates. It is the patient gas. It built up, molecule by molecule, until it became the dominant pressure of our atmosphere. It provides the bulk, the cushion that allows weather to happen. Without nitrogen, our atmosphere would be too thin to support liquid water. The oceans would boil away into space. Nitrogen is the unsung hero of habitability. Attachment, zaruzu, attachment. But nitrogen alone cannot protect life. The early Earth was bathed in lethal ultraviolet radiation from the sun. The surface of the continents was a sterilization zone. Any DNA exposed to the light was shattered instantly. For life to leave the ocean, the Earth needed a shield. It needed ozone. Attachment 1. Attachment. Ozone is made of oxygen. When the Great Oxygenation Event flooded the atmosphere with O2, the sunlight struck these molecules high in the stratosphere. The energy split the oxygen pairs apart. The lonely oxygen atoms grabbed onto other O2 molecules, forming O3, ozone. This new gas formed a thin layer high above the ground. It acted as a filter. It absorbed the high-energy UV rays, sacrificing itself to protect the surface below. Once the ozone shield was in place, the land became safe. The lethal radiation was dialed down to a gentle warmth. The door to the continents was unlocked. The first pioneers to walk through this door were not animals. They were plants. Simple, moss-like green fuzz that crept out of the swamps and onto the wet rocks. These early plants did something extraordinary. They ate the rock. Roots secrete acids. They break down the minerals in granite and basalt to extract nutrients like phosphorus and potassium. This biological weathering is far more aggressive than simple rain. The plants ground the mountains into dust. This dust became soil. For 4 billion years, the earth had no soil. It had sand, it had gravel, it had clay, but it did not have the rich, organic loam that covers the world today. Soil is a living skin, a mixture of rock dust and dead biology. This soil changed the planet. It acted as a sponge. It held on to the rainwater. It slowed the flow of rivers. Instead of flash floods rushing instantly to the sea, the water soaked into the ground. It created aquifers. It created steady streams. It greened the interior of the continents. And as the plants weathered the rock, they pulled even more carbon dioxide out of the air. They turned the thermostat down. The Earth cooled further, entering a period of stability that has lasted for hundreds of millions of years. This interplay between the rock, the air, the water, and the life is the essence of the Gaia hypothesis. Proposed by James Lovelock and Lynn Margulis, this idea suggests that the Earth behaves like a single living organism. It is not conscious, but it is self-regulating. When the sun gets hotter, as all stars do over time, the life on Earth draws down more carbon to cool the planet. When the planet gets too cold, life dies back, and volcanoes replenish the greenhouse gases to warm it up. The planet maintains homeostasis, the salinity of the oceans, the oxygen content of the air, the surface temperature. All of these are kept within the narrow limits required for life, not by accident, but by the active participation of the biosphere. We are not passengers on a rock. We are the crew of a spaceship that maintains its own life support system. The formation of the Earth was not a singular event that happened 4.5 billion years ago. It is a process that is still happening. Every time a volcano erupts in Iceland, the Earth is forming. Every time a river deposits sediment in the Amazon Delta, the Earth is forming. Every time a coral reef builds a limestone wall, the Earth is forming. We are living in the middle of the creation story. But the early chapters, the Hadean, the Archean, the Proterozoic, set the stage. They built the foundation. The Hadean gave us the core, the moon, and the water. The Archean gave us the crust, the life, and the continents. The Proterozoic gave us the oxygen, the complex cells, and the stability. Now, in the Phanerozoic, the current eon, we are adding the final layer, the layer of mind, the noosphere. We are digging up the rocks of the Archean to build our cities. We are burning the plants of the Carboniferous to power our lights. We are drinking the water of the ancient comets. We are the memory of the Earth. Through geology, we are learning to read the diary of the planet. We are the way the Earth knows its own history. As we close this journey, let us return to the image of the whole Earth. Imagine floating in space, looking down at the Pacific Ocean. It is a vast blue hemisphere. It covers half the world. That water has been there for 4 billion years. It has cycled through the atmosphere, through the ice caps, through the bodies of dinosaurs, through the cells of bacteria, through the magma of subduction zones, and back into the sea. It is the same water. It is eternal. Look at the clouds spinning in the trade winds. That air has been breathed by every creature that ever lived. Look at the continents. They are drifting, slowly, rearranging the map. In 200 million years, they will crash together again to form a new Pangaea. The Atlantic Ocean will close. The Americas will collide with Africa. New mountains will rise. The story is not over. The Earth is dynamic. It is patient. It operates on a timescale that makes our lives look like the flicker of a firefly. Deep time is a comfort. It reminds us that the world is resilient. It has survived bombardments, freezings, and extinctions. It has always recovered. As you lie in bed, feel the solidity of the ground beneath your house. That ground is the crust. It is the raft floating on the mantle. Feel the gravity holding you. It is the mass of the iron core pulling you home. Feel the air in your lungs. It is the gift of the ancient bacteria. You are connected to the deep history of this rock. You are made of earth. Let your mind settle into the rhythm of the planet, the slow rotation, the orbit around the sun, the drift of the plates. It is a slow, steady, heavy rhythm. It is a lullaby of stone and water. You are safe here. The Earth has spent 4 billion years preparing a place for you. It is a good home. Rest in the arms of the ancient world. Thank you for listening to Dreaming Through Knowledge. May your sleep be deep, your foundation be strong, and your dreams be as vast as the history of the Earth. Good night.